Last time I stopped at a point I was discussing the dynamics of the action of elements of the mapping class group on Teichmüller space equipped with Thurston metric. So I had a couple of more results to explain to you, but I wanted to do this more carefully because I want to take some time to talk about this. So you see, I explained to you that the classification of mapping classes into, well, we said periodic, reducible, and pseudo-Anosov. This was a result of originally from action on Teichmüller space union Thurston boundary. So this is Thurston's compactification. So we already talked about this. Of course, later there were same classification but using other actions. For instance, action on complex of curves. You can study you can say something using complex of curves and so on. Other spaces on which the mapping class group acts. There are several spaces. For each space, you can try to classify the dynamics of the action and to try to recover Thurston's classification. And anyway, so now what I'm doing here is to study this action with Thurston's metric. Here there's nothing metrical, it's purely topological. Here we are using, so the goal, in fact, we want to have something like, okay, this is good. So we want to have something like, say, classification of isometries, say hyperbolic plane. There are more complicated cases, but let's say this is our model, and so let me recall here what is happening. So we introduced something called the translation. Was it translation? Yeah, translation distance. So I have a homeomorphism of metric space, and then the translation distance tau of f. This was the infimum of the distance between x and f of x for x in my metric space. And okay, in the case of the isometries of hyperbolic space, you have what you call the hyperbolic isometries, where this translation distance is strictly positive, and when it is strictly positive, it is a fact here in hyperbolic geometry that there's an invariant geodesic, and then that the homeomorphism acts as a translation along this invariant geodesic, and the translation distance here is equal to this translation distance, and so on. And then you have the action on the you can complete the action by looking at these equidistant curves and so on. So this is the hyperbolic. Now in the general case, like in my case here, it's not. I mean, it's not necessary that there's an invariant geodesic, right? When this translation distance is positive, and the kind of question I'm asking there about Thurston metric is, when the translation distance is strictly positive, do I have an invariant geodesic, and does my isometry act as a translation along this geodesic? And the answer, in fact, in general, is no. This is why we have. I had my classification included in that case hyperbolic, and then there was a case called pseudo-hyperbolic, when this translation distance is strictly positive, but when this infimum is not attained at any point on the space. And it's interesting to study this more carefully and to see what are these possibilities. So let me just remind you of the other two cases in the hyperbolic space. In the hyperbolic space, we have these say elliptic, this finite order where there's a fixed point, and the isometry acts as a rotation along this rotation around this point. So I can put this point at the middle of the disk if I see the Poincaré disk, and then it's a real rotation. I see a Euclidean rotation, and then we have this parabolic element, parabolic elements where the action is, you have one fixed point here, and then these horocycles are preserved. The horocycles are preserved. We talked a lot about this horocyclic foliation of. So this is, you see, this is the case. This is a case where tau of f is 0 and not attained. And this is the case where tau of f is 0 and attained. So here it's not attained. You see we saw also this picture of this. You see, these are in the upper half plane. These are my horocycles. See, and this is like z goes to z plus a, say, and then so here a point here is translated by a distance, Euclidean distance a, and we know, we already discussed this, that the Euclidean distance when you go to infinity, it becomes from the point of view of hyperbolic geometry, this distance becomes smaller and smaller and smaller. So the translation distance is 0 but not attained. This is our model. It's a very simple model. In fact, if you go to hyperbolic space, say of dimension 3, then the situation is more complicated than than the one I described. But so okay. Let me make a small complement on Thurston's classification, so that also you see the complication. So Thurston's classification So in principle, this classification is distinct from the one using the translation distance, right? It has nothing to do with a metric. And our goal is to explain the intersection between the two, the topological classification and the metric classification. So let me say now a few words about Thurston's classification. So we have either finite order. So I told you this is when the action on Teichmüller space has a point, has a fixed point at the interior, and then it fixes it. You can realize this mapping class as a homeomorphism, well, as an isometry of a Riemann surface, and then we know that as an isometry, or if you want, as a conformal automorphism, and then we know that the automorphism group of a Riemann surface is fine. So this is finite order. Then you have the pseudo-Anosov. Let me write it here. Anosov. And in this case, you have this is Teichmüller space. This is Thurston boundary. Well, I explained last time that you have a fixed point on the boundary which corresponds to a measured foliations which has no closed curves, no closed curve at all. And since this is PMF, this measured foliation is preserved up to a constant factor. And then this constant factor must be strictly, different from 1. Different from 1. If the constant factor is equal to 1, then I fall into the finite order. This is not what I want now. So I have this fixed point here, which is, let's call it a pseudo-Anosov foliation. And then it follows from the theory, it follows from Thurston theory, that when you have this situation, then you have a second fixed point in the boundary. This is, let's call it FU. In principle, this one is called FU, the unstable foliation of the mapping class. Here it is another foliation, FS, the stable foliation. And then, while the dynamics of the mapping class is well understood. Every point here in Teichmüller space converges in the positive time to this unstable foliation, and every point on the boundary, which is distinct from this stable foliation, converges on the it stays on the boundary, of course, to this unstable foliation. You see, when I drew this picture, I was tempted, to draw an axis here between these two. But what is this axis? In fact, this axis does not make. This axis does not make sense unless I put a metric on the space, and then it will be the geodesic joining this point to this point for this metric. And if a geodesic exists for this metric, and what if several geodesics exist, and so on, and here is this analysis of mapping class group action on the Teichmüller space, the Thurston boundary. Suppose I have a pseudo-Anosov mapping class, or suppose I have a hyperbolic mapping class where the translation distance is positive is attained. Do I have do I have a geodesic? And then we talked about special cases of geodesics, which are stretched lines. Do I have a stretched line which joins these 2 points? This is also a question. Is this stretched line, is this geodesic unique, and so on? I mean, this is all the kind of questions which are in this paper which I mentioned to you. And I want to state these results. I want to state the results here, I mean some of the results. And let me mention, in fact, that this work here in this paper uses everything I told you before about limits of stretched lines and limits of anti-stretched lines and so on. Okay, this is what I want to. Let me state a few results now. Let me state a few results on this. Okay, this is also Thurston. This is Monday's seminar. This was Monday's seminar. Yes. Okay, so finite order pseudo-Anosov. Let me also mention here about Thurston's classification that I have also the reducible case. The reducible case means that on my surface I have a collection of simple closed curves which are invariant by my mapping class up to homotopy. In fact, they do not need to be. It is even reducible even if they are not, if they don't separate the surface. So this is a reducible case. And then let me just say about this reducible case is that the usual, I mean, what you do here is that you cut the surface along these curves, and you obtain a surface which is less complicated than the initial surface, and then you analyze your action, you analyze your mapping class action on this new surface. So this new, so here you are in some lower dimensional Teichmüller space. You're not analyzing the map in this. When you analyze this mapping glass group action on the Teichmüller space of the surface cut up along these curves, you're doing something in a lower dimensional Teichmüller space. So suppose when I cut these, then I get pseudo-Anosov, provided I know how to define pseudo-Anosov for surfaces with boundary and so on and so on. So I get a lower dimensional Teichmüller space. So suppose this is pseudo-Anosov with a pseudo-Anosov here with this dynamics and so on. This Teichmüller space is embedded in the big one, right? It's embedded in the big one. In fact, you see, there could be several pieces now of the surface, and I analyze in each of these smaller Teichmüller space my action. Suppose it is pseudo-Anosov, then all of them are embedded here, are embedded in this big one, and then I have the actions on the smaller Teichmüller spaces. I mean, the big codimension, smaller dimension Teichmüller space, and so on. And then the question is, of course, the question is what is the dynamics on the big one? What is the dynamics on the big Teichmüller space? Because you see a point here, and the big one also it's moved by this reducible, and then you have to. I mean, the situation is more complicated. You see, you have so these pseudo-Anosovs they have a dynamics here, and this one have a dynamics here on this smaller subspace. So what about this one? What about this point? What is he going? Where is he going? Is he going here or here or here? So all this depends on the relative dilatation factors of the pseudo-Anosov partial map. So here, remember I told you that there's a constant here. There's a constant here. Let's call it lambda, the dilatation factor, where this is for the pseudo-Anosov unstable foliation. This is lambda greater than 1, and here this is 1 over lambda for this one, and so on. So this is a rather interesting and complicated situation. So everything, of course, everything I said here from the topological point of view, we want to understand it from the geometric point of view. So what? So do we expect, for instance, to have Thurston geodesics joining these points and so on? Okay. I don't know the whole picture. In fact, this picture I never tried to complete it, but I can tell you what I know about this. I can tell you what I know about this. I mean, most of what I know about this is in 4 or 5 theorems, which I will state now. Okay. Let me introduce one more word. So this is F. Let F be a mapping class. Then the maximum dilatation of F is the maximum or largest dilatation of its pseudo-Anosov components. You see, I told you here that that there's a dynamics on the big space, and well, the result depends on essentially on what if this dilatation here is the dilatation of this smaller pseudo-Anosov is bigger or greater than the dilatation of pseudo-Anosov dilatation of the other one. So anyway, largest dilatation of its components. If there are no pseudo-Anosov components, then we take it to be 1. And then let me state these theorems. I mean, the first one is so let F be a mapping class. And lambda of F it's pseudo-Anosov. No, not so. It's maximum dilatation. It's maximum dilatation. The question now is, what is the relation between the tau of F and lambda of F? Tau of F is defined geometrically as the minimum translation distance, whereas lambda of F is a topological thing. It's just this thing which comes from the foliation of the pseudo-Anosov. And there is a relation, in fact. The relation is that there exists an n, an integer n, such that tau of fn, the translation distance of fn, is the logarithm of lambda of fn. This is the relation between the translation distance, the metric translation distance, and the pseudo-Anosov mapping maximal dilatation, the maximal dilatation of the pseudo-Anosov components. I don't think that you can take n equals to 1, and I think this is not an important issue, in fact. This n will exist in several theorems. It is, you see, when you're again, I make the same picture of the mapping class which is reducible. So the mapping class is reducible, and it could exchange components, right? But in order to say something reasonable, we want to take a power of the mapping class so that it fixes every component. And here I can talk about its action on that Teichmüller space. You see, so this is everything I said. I mean, there's and everything I will say. There's an n here, and this n is this one here. This n is this one. Okay, so now the next theorem. The next theorem is about mapping classes of infinite order. You see, after this translation distance, we want to study now what about the geodesics, and the result. Yes.
Ask about, so if 1n exists, then everything which is divisible by n also satisfies.
Divisible by n or multiple of n?
No, what is divisible by n? So some what?
All multiples of n.
Yeah, I think multiples of n. Yeah, yes, multiples of n. Yeah, everything which, yes, you're right. Yes. So if f is of infinite order, that is, if it is not periodic, if it is not, you see, as I said, the fact that a mapping class is of finite order means that it has a representative on the surface which is a homeomorphism of finite order. This is why I mean, I can talk about finite order or periodic. Okay, this is a theorem. In fact, it's a theorem of Nielsen saying that a mapping class, if it is of finite order, then it is represented by a homeomorphism of the surface of finite order, and then the extension of this theorem to other more complicated cases than finite order. I mean, finite subgroups. This was the famous Nielsen conjecture, which was proved using Thurston's theory and so on. I mean, this remark is has several developments, but this is not my subject. So if f is of infinite order, and if it leaves invariant a geodesic, then f is hyperbolic. So this is a hypothesis here which has the infinite order is Thurston's Thurston's classification. And so if it leaves invariant geodesic, then it is hyperbolic. And the translation distance well, on points, and the translation distance of points of this geodesic they are always equal to the translation distance of f. So in particular, if it leaves two geodesic invariant, then we always have the same translation distance on the two geodesics at every point of the two geodesics. And if you are interested in this is a question which we asked in the paper, and we don't know the answer to this question. So instead of infinite order, so if now I replace infinite order by hyperbolic, so the translation distance is positive and attained if f is hyperbolic. Does it have an invariant geodesic? The existence of invariant geodesics I can prove only in the cases, in a few cases, which I will tell you. So this is the subject of the next two theorems. So this is the case of pseudo-Anosov. You see, the pseudo-Anosov for some reason the Americans want to say pseudo-Anosov and not pseudo-Anosov, whereas in Greek is pseudo, in French it is pseudo. What about in Russian? Pseudo, yes, okay, so let's say, okay, pseudo. Let's say pseudo and not pseudo. So so what I was saying, yeah, I forgot what I wanted to say. That's, okay, let me state this theorem here. Yes, so when f is pseudo-Anosov, then it has these two invariant foliations, which are minimal foliations with no closed leaves. And the important thing is that it is a theorem from classical Thurston theory that these pseudo-Anosov foliations are uniquely ergodic. And you remember when I talked about limits of backward stretch lines and so on, there was a hypothesis on uniquely ergodic and not. So this is used here. This thing of uniquely ergodic. I mean, several things are used when I have a pseudo-Anosov. If f is a pseudo-Anosov mapping class, then there exists an n, well, an integer n, say greater than 1, such that Fn leaves invariant a stretch line. And here let me ask also a question. We don't know whether you can take n equals 1. This does not change a lot in the theory. In fact, this is this is not an important question, but we have this. And again, the proof uses the existence of these stretched lines when you take, I mean, you have to take the corresponding lamination to complete it. You see, the stretched line. Remember, you are more or less stretching. You are more or less stretching these ideal triangles. This is the most important idea in this theory. I said this several times. So you are okay. You have, and then you are combining them in some way, and then you obtain your stretched lines. So now, suppose you have a pseudo-Anosov mapping class. It has an invariant foliation, which, as we said, you can render it. You can make it geodesic. You get a geodesic lamination. You get a geodesic lamination. It's not necessarily, this geodesic lamination is not necessarily complete in the sense that its complementary regions are not necessarily ideal triangles. They may be polygons, ideal polygons, but they are not. They cannot be more complicated than ideal polygons, because if the lamination had more complicated components than ideal polygons, then there will be invariant closed curves. In fact, invariant simple polygons. We know that. So anyway, you have these ideal polygons, and you want to construct a stretched line whose limit point is this geodesic lamination. So the only thing you can do is to complete these ideal polygons in a random way. You have several ways, but finitely many ways, and then consider this stretched line and study what you have to deal. At some point, you have to deal with the fact that this you see. Your pseudo-Anosov map keeps invariant this lamination, but it could send this diagonal, which you chose randomly, to this one here. You see, right? There's no reason why it fixes this diagonal, which I added. But then you have to take, and this is where you need this. This is where you need this n. To construct this stretched line which joins your unstable and stable lamination of the pseudo-Anosov map. This is the n which appears in this theorem is this one here. Okay, so let me now state my last theorem in this. In this series. And this is a pseudo-Anosov map. In fact, it leaves invariant geodesic, some geodesic. You see, so it's not the same one I'm talking here. This is not the stretched line. Here, I'm not saying that. Not necessarily a stretched line. So this is another argument here. Okay, and maybe I have here. I want to. I mean, if you understand what I said here, I have this complement here. Leaves invariant a stretched line. This is and if, while the invariant lamination, invariant foliation, invariant measured foliation, either the stable or the unstable, the property is equivalent for the two. If it's measured foliation or lamination, is complete, then I can take n equals 1. So here, under a special case, under a special hypothesis, I have this this theorem here where pseudo-Anosov leaves invariant. In fact, I can replace a geodesic by a stretch line, a geodesic which is a stretch line. I want to mention now something important. I mean, for the motivation of all this. So this was motivated, this work was motivated by an analogous work motivated by work of Bears. I think it was in, let me conjecture that it's 1976 plus or minus 1, I think. The paper appeared in Acta Mathematica, where he does the same thing for the Teichmüller metric. He studies the geometric action of the mapping class group and the geometric, I mean the classification of mapping classes according to their action on Teichmüller space equipped with the Teichmüller metric. And maybe I should mention also that this is now the year here is unknown, maybe 2012 and so on. There was a paper, another paper, I think it appeared in American Journal of Mathematics, and this is by Papadopulos and Wentworth. And this was the same thing for the Weil-Petersen metric. The same kind of discussion for the Weil-Petersen metric. And you have not exhausted all the metrics with this, all the metrics on Teichmüller space. You see there are many metrics which are open to investigation. Somebody told me there are 12 known metrics. I mean, the papers written on 12 metrics. I cannot tell you what it is. I mean, I know some names. One is called the Liu-Hsu metric. Another one is the McMullen metric. And then there are there's a metric called the maybe I will mention it later, called the length spectrum metric, which is a symmetrization of this Thurston metric. I mean, everything we said, you remember, I think you remember that these metrics here are symmetric. The distance from x to y is equal to the distance from y to x, whereas the Thurston metric is not symmetric. The distance from x to y is usually not equal to the distance from y to x. You symmetrize it, you get another metric, which is called the length spectrum metric, and you can try to do the same thing for the rest length spectrum metric. I don't know. This is something open. I want to, so before the break, I want just to recall, because I will use it in later. I will use it in the second part. We talked about the Teichmüller metric, but I never gave you a definition, and I want to give a definition. I want to give a definition which is not the usual one, and I hope it is correct. I mean, I hope it is not too restrictive. So remember this Thurston metric, we defined it as by comparing lengths of simple closed curves, but also it is obtained by comparing by taking the best Lipschitz constants of these maps. So here a metric, the Teichmüller metric well, it uses the dilatation of maps, in fact of homeomorphism, but I want to suppose that my map is a diffeomorphism. And the dilatation is easier to define. So this is infinitesimal now. So when we have diffeomorphism, we can use infinitesimal dilatation instead of global Lipschitz constant. This makes the things very, I mean, much easier. So the dilatation of F. So this is like in Thurston's metric. I have gamma, the supremum over gamma. No, there's no gamma here. The supremum is over x in S. In the Thurston metric, I had x and y, and then I had to write here some Lipschitz constant. But here is the supremum over x, and we are taking infinitesimal dilatation. So this is the supremum of this quantity here. The supremum of the dfx of u, this is the derivative of taking diffeomorphism, and this is u over u in the tangent space, and norm of u equals 1. And here I take the infimum of the same thing, the infimum of the same thing. And here I'm taking f, say, from between a surface S equipped with a metric G to the same surface F equipped with a metric H. And here up there I'm using the metric H, and down I'm using the metric G. You see, to define, in principle, to define the dilatation of maps, let's call it quasi-conformal dilatation in order not to confuse it with the Lipschitz dilatation. In principle, F is a map between two conformal structures. I don't need any metric here. I don't need to talk about this. I don't need to talk about norms and so on. I mean, it's only conformal geometry. But this definition is okay also, because in each conformal class of in each conformal in each conformal structures, I take a metric. I take a metric, say a Riemannian metric, whose underlying conformal structure is this one, and then another conformal structure. I take a metric H, Riemannian metric, and so on. And so this is the definition of the. It is the definition of the quasi-conformal dilatation, and of course the Teichmüller distance now, the Teichmüller distance between two conformal structures or two metrics. Here I took metrics, but in fact everything is, you can replace by conformal. So this is this is the infimum now over F of the. I think I should put some logarithm somewhere. Let's put it here. this is greater than this, so this is greater than 1. The ratio is always greater than 1, so I can put the logarithm here. And well, okay, that's it. So this is a formula which is analogous to Thurston's definition of his metric, because it uses the infimum of, I mean, the best quasi-conformal dilatation of a map, and so on. And this is, and you see, I look at my notes from time to time because I'm always against formulas, and I never remember formulas. But here I see that there's a 1/2 for some mystical reason. There's always a 1/2 here. And this is symmetric. This is symmetric, contrarily to Thurston's metric. So I told you that there were several instances where we can try to define a Thurston-like metric, and I want to talk about this topic on Thurston's metric on the Teichmüller space of the torus. So here we have this surface of genus 1, and we are comparing say flat metrics. Comparing flat metrics on this torus. We want to put a distance among these flat metrics, and then study the geodesics, study the automorphism, and so on. I mean, all the questions we have. Study the study the length spectrum, compare it to the best Lipschitz constant, and so on. So let me. So there is. We started a theory. I mean, we built. There's a paper on this. It could be. I mean, there could be some sequel, which we never did. I mean, there are still some questions. This is a paper. I think I mentioned it when I made a list of papers. This is a paper with Belkirat and Troyanov. This is Troyanov. We were talking about these Russians who emigrated, but Troyanov is his grandfather who has emigrated in the 1920s, in fact. He's completely Swiss. He doesn't, and he's my good friend. Okay, so we have, and this appeared in 2005 in Transactions. Okay, so we have S, usually T2 is the 2 torus, and we consider the space f of S, space of flat metrics, Riemannian metrics of constant curvature 0. So you see the torus, I mean, you have these geometric structures on the torus, and then you know that you have these flat metrics obtained by gluing the two sides of a rectangle or a parallelogram like this, Euclidean parallelogram. You have different shapes of parallelograms, so you have different kinds of metrics on the torus. Some of them have very short geodesics. Some of them do not have short geodesics, and so on. They are all different. You make a space of all of these. This is a hyperbolic. This is the Teichmüller space of the torus, and it is known that the space of all metrics is the hyperbolic plane. What does this mean? In fact, there is the Teichmüller space of the torus is the hyperbolic plane. There are several ways to see this. One way is, one way is, you see, I just defined the Teichmüller metric before. The Teichmüller metric on this space of flat metrics of the torus is the Teichmüller metric is the hyperbolic metric. Okay, this is a well-known fact that the Teichmüller's metric of the torus coincides with the hyperbolic metric of the hyperbolic plane. And this was known. In fact, it is in this 1939 paper by Teichmüller. He has this long paper, 170 pages, where he develops the basic of Teichmüller theory, and he treats the case of the torus in several sections, and he proves this, that the Teichmüller metric of the torus is a hyperbolic metric. So now we are interested in the Thurston metric. So I will say several things about this Thurston metric on the torus, but let me announce this result right away, that the Thurston metric of the torus is the semi-Apollonian metric on the Thurston metric of the Teichmüller space of the torus is the semi-Apollonian metric of the upper half space. So what is the semi-Apollonian metric? This is something I mentioned very long ago. The first week I came here, I talked about this. So let me tell you what it is. We have the upper half plane, and we take 2 points, say x and y, in the plane, in the upper half plane, and we define the distance between x and y to be, so there should be a logarithm somewhere, log of the supremum. In fact, this is the supremum of the distance, Euclidean distance from x to a, divided by the Euclidean distance from the y to a, and this is the supremum over a on the boundary of this upper half plane. Let me check if everything is okay, because I told you that formulas are not my strong thing. I think I didn't write this up. Okay, this is this is correct. This is correct. In fact, my question was whether I put x here and y here, but this is correct. Notice that in the definition of the Thurston metric, usual Thurston metric, you have the distance of f to distance from f to g. You have the logarithm of the supremum of the length of g. You put f to g, you put g above and y below, whereas here you put it in this way. If you change x and y, if you interchange, and then you obtain another metric, which which you can study. But this is the semi-Apollonian metric. Notice that. Okay, so this is a formula. This is a very easy formula, in fact. This is a very easy formula. It gives you a non-symmetric metric on the upper half plane. It's easy to see that it's non-symmetric. It's also easy to see that the distance between x and y may be 0. This metric does not separate points, in fact. And I think if you take x here and y here on the same line, then the distance between x and y is 0.
Vice versa.
Or vice versa. Yeah, it's vice versa. Thank you. Yeah, I was.
The distance to the hand.
Okay. So this Thurston metric on the Teichmüller space of the torus has this weak property that it does not separate points. The next thing which is interesting here is that the symmetrization of this metric is the hyperbolic metric. Of the upper half plane. And therefore, because of what I said here, the symmetrization of the Thurston metric in the case of the torus, this is the Teichmüller metric. Something which is not correct in the case of surfaces of higher genus. I mean the usual Thurston metric. Its symmetrization is not at all equal to the Teichmüller metric. This you can check. You can check easily, in fact. So I will say several things about this, but let me just. I wrote two formulas somewhere. Okay, yeah, they are here. So I will copy my formulas. How do you see this? How do you see that the symmetrization is this? In fact, this is because this semi-Apollonian metric, in fact, you can write a formula for this. And, the formula is this one. Okay, I don't have the same notation here. Let us use this. Let us put it z and z prime. Because I want to use complex variables, and so this is z and z prime. Okay, doesn't change anything, but let us use z and z prime. And here this is. Working a little bit with this, you see that this is equal to z prime minus z bar plus z prime minus z minus z bar. You should check this because I always make mistakes with formulas, and also because I don't have my glasses now. So it turns out that this is equal to this, and then when you symmetrize this, you see the symmetrization is half of the symmetric of x and y is half of distance from x to y plus distance from y to x. So this is why there's a half here, and this is the logarithm of this becomes the logarithm of z minus z prime bar plus z minus z bar over z minus z prime bar minus z prime. I don't know. If you take notes, so please check this. I mean, for me, writing this formula is like writing Chinese. But I know that some people want to see the formula. So this, when you symmetrize this, you get this, and it is known that this is the usual Poincaré metric of the upper half plane. So this is okay. I will tell you more or less how we obtain this. And I will tell you first how you define the Thurston metric in the case of Teichmüller space of the torus. So let us start by where is this? Let us start by defining recalling this definition of this Teichmüller space. So I said I have f of s. These are the flat metrics, space of flat metrics on S, and then we want to. I mean, it's natural to say that two metrics are the same if they differ from each other by. I mean, we don't want to. We want the tori to be of the same form, and form is invariant by scaling. So we want to mod out by the action of the strictly positive reals, and then like in the case of surfaces with boundary. Sorry, I don't have boundary. Surface boundary will come later. So, like in the case of surfaces, hyperbolic surfaces with higher genus, we will mod out also by homeomorphisms, diff zero homeomorphism. Is this okay? I'm seeing you are checking this. Was this okay? Okay. Okay. So this is the space which is identified with the upper half plane with in several ways. Yes. Yeah, this one. You see, I have one way is one of the usual ways is the fact that the just to see a torus with a flat metric as the quotient of the Euclidean plane by a discrete group action which I call gamma AB. So this is a translation group of translations. This is M TA plus N TB. These are translations, and A and B are linearly independent vectors. And there are I mean, there are essentially two normalizations. One normalization is that you can make this vector A to be norm 1 instead of there's this normalization where I said you scale the matrix, so you can make this you can use it here to make this vector A of norm 1 and then rotate so that this vector A is the vector 0 1 in the Euclidean plane, and then you have the other vector, the vector B. I mean, it could be also down, but I don't want to talk about this. I mean, there's something about orientation here which I don't want to deal with. So the vector B, the vector B will parameterize all the tori, and the vector B lives in the upper half plane. Okay, this is one usual parameterization. Another one is when you represent A and B as the columns of 2 by 2 matrices, and then you have then you get SL2R, and then you want to divide by the group of rotations, which is SO2, and SO2R divided by SO2. This is also a homogeneous space, which is also the upper half plane. I mean, there are other kinds of things you can do, but now no, this is not the right one. This is the one. Yeah, and then we have to talk when we. So we're talking about metrics on a fixed torus, or metrics on or having a surface, a topological surface with and then the variable, I mean the elements of your Teichmüller space are surfaces equipped with a flat metric. So, and then you have a privileged homotopy class of homeomorphism between the fixed topological surface and this variable geometric surfaces and so on, like in the usual theory. So this is a theory. This is a theory of marking. This makes your surface marked surfaces. I mean, what I want to stress is that this marking of the torus, instead of choosing homotopy classes of maps, you can just choose homomorphisms from the fundamental group of the torus, of the fixed torus, into the fundamental group of the variable torus, which is a geometric torus. And this is the kind of marking which Teichmüller uses in his paper, which he doesn't use markings by homeomorphism, but by homomorphism between fundamental groups. And everything I'm stressing now is that these two vectors A and B, we know what we are talking about. When I talk about A and B, I mean it's not. We know that we have these two vectors in any torus. This is important. And then let me define this first and distance now. Let us write here. Let us write this here. So I have a formula. Okay. Let us call them G and H. This is the supremum gamma. This is the set of homotopy classes of simple closed curves in the torus. I'm using the same formula I used for the case of surfaces of higher genus. And then I have a logarithm here as usual, sup of log. And here, well, this is LH of gamma divided by LG of gamma. And then the normalization, if I use this definition here up to the action of the positive real numbers, I want to divide by the length of a fixed homotopy class. So this is the length is the minimum length in the homotopy class. So it means the length of a Euclidean geodesic, which in general is not unique, unlike the hyperbolic case, but they all have the same length. And here I'm dividing by the length of a fixed curve, which I want to think of as this curve gamma here. If I don't make this normalization, then I have to divide by the length of this curve. If I make the normalization, then this is equal to 1. I mean, the formula still holds, but this is redundant, but this is fine. So this is the definition of the metric in terms of the lengths of simple closed curves. And then I have the other definition, L of G of H okay, this is the infimum of over F isotopic to the identity. And here, this is the log of Lipschitz, the Lipschitz constant of F. And now again, in the case of the torus, the Lipschitz constant of F, I have to, so this is the usual definition of the Lipschitz constant that I used in the definition of the usual Thurston metric, but there's something additional here. So Lipschitz of F, this is the supremum for X different from Y of so D, this is D of F of X F of Y divided by D of XY, and this is divided again, I divide by the same thing, L of epsilon, this is L of epsilon, and in the numerator everything, the lengths and the distances are with respect to the metric in the range, and in the denominator the definition of the in the definition I use the metric in the domain. So everything is exactly as before, especially the definition of this Lipschitz constant. I have to make a normalization, and then the theorem, one of the theorems.
It
yes.
Depends on the choice of epsilon.
Yes, but I said that epsilon. Yeah, you're right. It depends on the choice, but epsilon I take it once and for all, and I want to think of it as this one here. You're right. Yeah, absolutely right. I take it the same there and here. Yeah, I take the same. I have to take the same epsilon to have this theorem here. The theorem is that L equals K. So this is a result which is analogous to Thurston's result, which I did not prove. In fact, I prove only the proof of L equals to K in the case of the Thurston metric for surfaces of higher genus is a complicated proof. In fact, it takes several pages, and it's in Thurston's paper. If you want, you can read now this Thurston paper and compare with what what I told you, but I tried to explain the things which which I know how to prove because there are things in my papers. This theorem, I mean, after some years, I understood the proof, but it's a complicated proof. Anyway, so the proof here is easier. The proof in this case is of the torus is easier, and then we have the notion of, let's make it here as theorem 2. Minimal stretch maps. The maps, minimal stretch maps exist. The maps which realize this infimum exist, and these are the Teichmüller maps. These Teichmüller maps this means the so you have two tori which you represent by parallelograms, and these Teichmüller maps, forget about the word Teichmüller, these are the affine maps, the usual affine maps.
Along the y-axis.
Huh? Along the y-axis.
Yes.
Well, the affine maps between two parallelograms, you have a distinguished you have a distinguished map which is the best affine maps. Yes. Yeah, between the parallelograms, and then they go down to the maps between tori. So, and are the Teichmüller maps, and then you have the minimal stretch rays. It is when you multiply when you stretch your affine map by the affine map, you have a constant of dilatation. When you vary this constant of dilatation, you have rays which we call the minimal stretch rays, and these also exist, and these are what is usually called the Teichmüller rays in Teichmüller space. So this is I told you that the symmetrization is the Teichmüller metric, but for this you don't need to symmetrize. They exist already in the non-symmetrized version. I want to show you just a little bit. I want to show you how you prove this fact. I said that the Thurston metric coincides with the semi-Apollonian metric because the proof is, the proof is easy. It's not difficult. It used just some trick, and I want to make a comment on it. I want to make a comment. Yeah, I'm not sure I want to go through all this. Okay, so let's do the outline. So we have C divided by. Let's look at it this way: C divided by zeta plus zeta of z. So this is my torus. Before I have this normalization where this is 1 and this was b, but now I call it zeta because I want to use complex numbers. So this is a torus. I represented like this, and then I come to this formula there of the lengths. So we have two tori, zeta prime z, And let me write again the distance between them, the distance between, so I call this zeta and zeta prime. Okay, this is log sup. So you see, I want to cancel the LH, the L zeta prime of epsilon and L zeta of epsilon because I'm using this normalization. So this is just L zeta prime of gamma, L zeta of gamma, and this is supreme over gamma, simple closed curve gamma. And now the important thing is that these simple closed curves gamma on the torus, you see, you can see it first on this square torus, and then on the other tori it's the same. So this is parametrized by two integers m and n. In fact, where m over n is the slope. Okay. Okay. So you'll see why I'm doing this. You will see why I'm doing this. So this becomes yes, and then yeah. Okay. So this is one thing. This is one thing, and the other thing is that the minimal length, you see this length of the shortest curve in gamma is just when I make gamma linear, when I make this. So m and n, you see, I make them every time I have m and n, I have these homotopy classes of curves which join this point to this point. I have parameterized by m and n, but the minimal length is when I make them geodesic, and this is equal to exactly to m plus n zeta. Okay, this is the length of the closed geodesic in my class, in my homotopy class. Okay, and now this here becomes log sup. You see, this is a very simple calculation, but it's for me it's always a kind of miracle. This is m and n in z, and this is m plus n. I mean, this is the norm of the complex. The norm of the complex number. So you can call it absolute value. Some people call it absolute value. And this is, my handwriting is very large. I need still one line. And now this is the very simple trick. In fact, this is log sup now here I put m over n plus zeta prime divided by m over n plus zeta, and I take the absolute values, the moduli of these complex numbers, and so this is for m and n in z, and this is the same thing as the log of the sup of in fact, let me write the same thing. This is q plus zeta prime divided by modulus of q plus zeta, where now q is a rational number. Okay? And now I don't change anything if I replace rational numbers by the real numbers, and I get exactly my semi-Apollonian formula. And this is interesting for me, you see, because in Thurston's theory, you start with defining this formula for the distance function by taking supremum over simple closed curves and so on. But then you know that the set of simple closed curves, I mean in the Thurston projective measured foliation space is dense, and then you extend the length function to geodesic laminations instead of lengths of curves, and then you end up with a formula where here instead of simple closed curves you have geodesic laminations, which is very good, in fact, which is very good because this space of geodesic laminations is projective geodesic laminations is compact, and so this supremum attains a certain value at a certain geodesic lamination, and this geodesic lamination is the geodesic lamination which realizes the supremum of this the supremum of this ratio, and it is the geodesic lamination is the measured geodesic lamination. In fact, I said it is measured geodesic lamination is the one which is most dilatated, and it gives you a direction in Teichmüller space. You see, you can see this projective space of measured geodesic lamination sitting in the boundary at infinity, and this one gives you the direction where you have to stretch. And the theory, I mean, Thurston's theory is based on this. You see, it's based on this, where the Thurston's theory, for instance, where he wants to prove that any 2 points are joined by a geodesic. Then you have to start with this. You have to take the maximally stretched lamination. You have to start with it, take this direction, and there's a complication there where sometimes you have to change direction. But this is, I mean, all this is. You can see it in a simple way on this Teichmüller space of the torus.